So one of the things I do want to mention to you guys is up to this point, we really haven't done a lot of physics yet. You've really been doing a lot of math practice. We've been figuring out how to deal with vectors. That's math. We've been figuring out how to deal with Galileo's equations for falling bodies. That's basically math, doing a lot of algebra. And trigonometry, math. Now we're going to really start delving into some physics, actually, and kind of what's going on. And we're going to talk about motion. That's where we're starting, is how things move. Galileo described for us basically how to describe motion. He gave us equations to describe velocity and displacement and acceleration, but he never really told us what causes that motion, and that's what we're going to start dealing with today, Newton's laws of motion, and there are 3 of them, okay? But before we get there, we're going to backtrack a little bit. I'm going to give you a little bit of history, and I'm going to give you a little question here, first of all, okay? You shoot a little gun into a circular tube, the bullet goes round and round and round, and then it comes out of the tube here, okay? Think about whether you think it will follow path A, path B, or path C. And let us vote on it now. Raise your hand if you think it'll go in path A. Path A. 1, 2, 3, 4, 5, 6, 7 of you. Okay, cool. Path B. 1, 2, 3, 4, 5, 6, and path C. 1, 2, 3 of you. All right. Okay. So I'm not going to tell you the answer right now, but by the end of this PowerPoint, which we probably won't finish today, we'll figure it out. So you have some time to think about it. Let's go way back to Mr. Aristotle. And again, I'm not going to test you on this historical stuff, but I want you to think about it. Aristotle was one of the first people that we're aware of that tried to describe how things work in the world around him. Okay, and he tackled the idea of motion. And here's kind of his thinking. If he picked up a rock and dropped it, this is not a rock, but it's a ball, but imagine, okay, use your imagination, this is a rock. He dropped it, he noticed that the rock would fall, okay, and if it was a rock, it would just fall. He also noticed that, like, when he had a candle, if he blew it out, the smoke would rise. He wondered why that was true, and he basically came up with this idea. Back in the days of Aristotle, there were 4 elements. They didn't have a periodic table of the elements, of hundreds of elements. There was 4. There was earth, fire, water, air. He came up with the idea that things have a natural tendency to do what they are inclined to do. That's what he called natural motion. When I drop a rock, it naturally wants to fall and be at rest down on the ground because it's made of earth. And that's where the earth is, and the earth is stationary. Things that are made of earth would like to be stationary. I can't move my rock unless I push on it. Smoke, on the other hand, is made of air, and air is above us. Therefore, when I blow out my candle and the smoke rises, it's doing that because it naturally wants to rise and be in the air where it is from, right? That's what he called natural motion. He said in order to make things move, like my rock, I have to push on it. He called that violent motion. It was an interesting concept, incredibly wrong, but it was an interesting concept. And it was kind of cool because it was the first person that tried to explain it. Copernicus comes along a few thousand years later, and he says, you know what, the Earth's not stationary, you guys. You know, I know Aristotle told us that things want to be still because they want to be like the Earth. But the Earth's not stationary. It's actually spinning once every 24 hours, and it's rotating around the sun once every year. And so, you know, that doesn't work so well. So that's a bummer. Okay. So then Galileo comes along. Yeah, Cameron.
Are we going to need to know the history for any test papers?
No. Just to be a better person. Okay? So Galileo comes along, and he actually starts thinking a little bit deeper about this. And here's what he thinks. He takes his little soccer ball of science, and he puts it on the table, and he pushes it. And he notices that it stops. And he thinks, well, that's kind of cool, but what if I got some sandpaper, and I really, like, polished my table and made it even smoother, and I pushed on my soccer ball? What would it do? It would go further. And then he thought, okay, cool. And then what if I got, like, some silicone lubricant, and I sprayed it all over my really smooth table, and I pushed it? What would it do? It would go even further. So he realized that the soccer ball really doesn't want to stop. When I push it, it wants to keep going, and the thing that stops it is friction. Okay, exactly the opposite of what Aristotle said. Aristotle said, hey, this thing wants to stop unless I push it. And Galileo said, no, you know what, if I could get rid of all the friction, then actually when I pushed on it, it would just keep going forever. Totally different concept, much more accurate, okay? And so he didn't have a little soccer ball of science like we do, but check it out. I can remove much of the friction, and it keeps going, right? It keeps going right across the floor. Okay? No friction, it wants to keep going. See? It just goes forever. Okay?
Keep it on the entire class.
Yeah, that would be really bothersome. All right, so this is an incredible discovery that Galileo came up with, and it basically is the foundation for Newton's first law of motion. Newton did credit Galileo for his idea with the first law of motion. So let's move forward and to talk about Sir Isaac Newton. So there's Isaac. What do you think about this guy for a second? He was incredibly smart. If he was a student in this class, first of all, he wouldn't want to sit next to any of you because he would pretty much hate you all for being such idiots. And he would be right because he would be much smarter than you. And he would be much, much smarter than me. He'd hate me too. He'd think I was an idiot. And he would let us know too. He would scoff. He would be like, "Oh, you guys are fools." And we would all hate him and want to hurt him. But he would show us up intellectually at all times. Okay? He absolutely had no social skills. He was horrible in personal interactions, but he was brilliant. Think about this for a second. He was discovering relationships for the world around him and trying to explain them, and there was not a mathematical way to do it. So he invented calculus. Okay? He invented math to do the physics that he needed. All right? It's crazy stuff. So, and technically someone else did invent it at the same time. So there's two people that kind of work on it, but he was one of the main people.
Doesn't he look like Zeke Jordan? Absolutely.
Exactly.
Really? Okay.
His personality sounds like
That's interesting. Okay.
Thank you, folks.
So, Newton's first law basically is an outgrowth of Galileo's idea, and we call it inertia. And inertia is something that you are immensely familiar with, okay, because you're a teenager. And teenagers have lots of inertia. When you're feeling excited and energetic, nothing can stop you, and you guys are running around and like you're going. But when you're sitting on the couch with the remote control in one hand and a bag of potato chips in the other hand, you do not want to move. And your parents come in and say, "Get off the couch, you good-for-nothing bum. Go out and mow the yard." And you're like, "Oh, my God, I don't want to move." That is inertia, okay? The idea that something that is not moving doesn't want to move, and something that is moving doesn't want to change its motion. That is Newton's first law of motion. And here's how he said it, more or less. He basically said, every object continues in a state of rest or of motion in a straight line at constant speed unless it is compelled to change that state by forces exerted upon it. Okay? We've kind of summarized that a little bit more briefly here, so rather than writing all this down, why don't you write this down? Okay? He was English, British. He grew up in London and outside of London, I believe. A body at rest stays at rest, and a body in motion stays in motion unless acted upon by a net outside force. This is Newton's first law of motion. Oftentimes it's called the law of inertia. Now there's a couple things we need to make sure we understand clearly about this law. When a body in motion stays in motion, what kind of motion does it stay in? Uniform what? What does that mean? You're right. What does uniform motion mean? Constant velocity, which means it's in a straight line with a constant velocity. Uniform motion. It's not accelerating. Okay? Cool. Unless there's a force causing it to accelerate. The other word we need to make sure we understand is net. What does that mean? Total. Exactly. Total. You need to look at all the forces acting on an object and add them up, remembering that forces are vectors. And what you get, the resultant you get, is the net force acting on an object. All right? So here you are sitting in the chair right now. Are there forces acting on you? Yeah. Are you moving?
No.
Other than like twitching and stuff like that? Or you're not really moving anywhere. Okay? So if you're sitting there and you're not moving aside from the earth spinning and all that other stuff that we could talk about, but let's don't talk about that for a second. What forces are acting on you? What direction is gravity acting on you? So gravity's pulling you down. Why aren't you falling down? What? The chair. What's the chair doing? Pushing back up. It must be pushing up with the same force that gravity's pulling down, so that when I find the net force, there is none. And that's why you're not moving. Okay? Newton's third law is kind of that. Yes, it is kind of that. For every action, there's an equal and opposite reaction. But there's a subtle difference there that allows things to move sometimes. Okay?
Is that chair actually pushing up?
You bet. Yeah. Okay.
So what's the
Okay, so let's look at this concept of force then. So Newton introduces this idea of force. An object at rest will stay at rest, or an object in motion will stay in motion unless acted upon by a net outside force. So what is a force? How would you describe what force is? What do you think? Yeah. Okay. This is what Jedi's have. It is incredibly hard to describe what force is. Real basically, it causes, it's like a push or a pull is one way of thinking about it. But it's more simple to see what forces do than to try to tell you what a force is, okay? It's easy to see the effect that forces have on things. If a force is being exerted, it either causes a change in velocity of an object or it causes some sort of deformation of that object, okay? It's kind of what forces do.
How would you describe what the force is?
Okay. The one thing that you're going to need to remember, we've been working on vectors, and lo and behold, yes, force is a vector. In order to find the net force on an object, you must add all of the force vectors that are acting on it and find out what the resultant is. And the resultant is the net force.
Can we do a lab on that this one?
Tried to. Yeah, we tried to. If the net force on an object equals 0, that's a special situation. If I add up all the vectors and I don't get anything, I get 0, then we have a word for that. And the word is equilibrium. Okay? When all the forces on an object add up to 0, we say the object is in equilibrium. And what is an object doing that is in equilibrium? And so what is it doing? Staying still or? Excellent. Or moving with a constant velocity. That's Newton's first law. If I have a net force of 0, my object is either standing still or it's moving with a constant velocity. Okay?
Yeah, when it's not like all the way. But there
must
have been already some time in the past.
Right, but we're not talking about that. Yeah. But right now, if I have something moving through space in a straight line at a constant speed, the net force on it is 0. Okay? This little symbol here means... Yes, exactly. It's just chilling. This little Greek letter sigma means sum. Okay, for those of you that are taking calculus, you'll see this signal. You'll see this symbol a lot. But basically, if I add all of the forces and they add up to 0, the object is in equilibrium. That's what that is telling me. Okay. Sum, the sum of, add everything up. Yeah, I'm sure you could, probably. Yeah, you can. Oh, like, can you make that symbol?
Yeah.
Yeah, on Word, you have an insert. Free body diagrams are something that you are going to do frequently. You'll have a question that says, hey, draw a free body diagram of something. And what they're asking you to do is to draw the force vectors acting on that object.
I like saying, like, I pushed this at like 10 newtons, you got the box
And the force vectors acting on it. Exactly. Okay? Remember, when you are drawing force vectors, the direction is important. The length of the arrows is important as well. If one force is bigger than another, it should be a longer arrow. And you should also label what that force is when you're making a free body diagram. Already there was?
Yeah, it was like that.
Okay. Don't give Nick a hard time. We gave him a hard enough time last fall. Okay. Here's the mystery surprise box. Notice that this is a free body diagram of the mystery surprise box. There are 4 forces acting on it. Okay? We have gravity, which always acts downward towards the center of the Earth, and it's labeled mg. We'll talk about why that is later. You're familiar with g. What was g? What of gravity? The acceleration of gravity. Mg is the force of gravity. Okay? You need to understand the difference between force and acceleration, and we'll talk about that. Notice that this box is not falling down. Why is it not falling down? The table is exerting a force. Okay, now the table can't exert a force sideways. It can't push sideways. It can only push perpendicular to the surface, back up. And that has a special name. When a surface pushes back up perpendicular to itself, it's called a normal force. The word normal means perpendicular, and you'll see this a lot in physics. Draw the normal force, or what is the normal force, or what is the normal reaction force. Okay, and they're talking about the perpendicular force to the surface. Cameron. Here's two people pulling on a big old crate. Is there a net force? Yes. And how would you find it? Add some vectors. Please do remember that they are vectors. If I showed you this picture and said, what's the net force, and you said 200 newtons, I would be really sad, okay? Because vectors are different. You have to add the vectors, right? So we'd go 100 to the right, 100 to the up is equal to the square root of 2,000, right, to the up and right, right, at an angle of 45 degrees. I don't know, what's 100 squared? 100,000, is that?
Well, it's 102.
Now here's the mystery surprise box again. Let's look at a couple things here. Mystery surprise box is sitting on a table, and I'm pulling on it at an angle. Ooh, vectors. Vectors, vectors, vectors. Take a look at what we can do here. Can you please, let's just for fun find this. I'm pulling at 40 newtons at 30 degrees. Please solve for the x and y components of that force. Please tell me how hard I'm pulling in the x direction, how hard I'm pulling in the y direction. Okay. So this is 40, and this is 30 degrees. What's the x and y? Yes.
The X is 34.6. And the Y is 1. No.
Okay. So now let's look at this for a second. Imagine my box weighs. Let's see how much it weighs. Let's say it weighs 45 newtons. Okay? The force of gravity is 45 newtons. Therefore, if I'm not pulling on the box, what's the force normal going to equal?
0.
The force normal?
45.
45 newtons. Okay? The table will push back up with 45 newtons and everything's hunky-dory. Then I come along and I pull on my rope, and you just told me I have an upward pull of 20 newtons. Now what's the force normal? Now how hard's the table pushing?
Oh, it's still 45.
45 down. I'm pulling 20 up, and it's not going up or going down. Therefore, what's the force normal? No.
Oh, it's minus 45 minus 20.
Which is? Thank you. 25 newtons. I've got 45 newtons down, and now I've got 45 newtons up, and the box is still standing still. Does that make sense?
Yeah.
But I'm also pulling with 35 newtons to the right. So unless there's 35 newtons of friction, it will be sliding to the right. Okay, in general, there are two main kinds of forces, you guys. There are what are known as contact forces and long-range forces. A contact force requires physical contact, right? So, you know, I get really mad at Eli over here and I want to smack him in the face. I can't just stand here and smack him in the face. I have to walk up and actually contact him to exert that force, okay? Right? Now, if it's different, right?
You could shoot a bow and arrow.
Right, but the arrow would have to contact you to exert the force, right? Some forces don't have to do that, okay? No, wind still has to contact things. Gravity, I'm thinking of. Gravity, right? The sun is pulling on the earth gravitationally from 93 million miles away. There's no contact there, but it's still pulling on the earth, okay? Technically, the electromagnetic force acts over a distance, but, you know, they all act over.
Oh, yeah, like magnets.
Yeah, yeah. And if we start looking at what happens in the universe around us, the motion of all objects, we can pretty much explain everything with four forces. And this is pretty remarkable. If you think of every action that happens in the universe can be explained with four forces. It's kind of cool. There are physicists that believe that that shows us that we don't know very much. Because if we really understood the universe, we would be able to explain it with one force, with one theory. And we don't. We have four theories. String theory is trying to do that, okay? But we really have four fundamental forces. And the idea of unifying these forces is a huge quest for some people. It's called there's a theory called the grand unification theory that people are looking for. But right now we know that there's four. What are the four forces? Gravity is one. No, that's just a general kind of type of force.
Physical, like.
No, gravity. Electromagnetism is another one. No, that's a kind of electromagnetic force. No. Gravity, electromagnetism. The other two act inside of a nucleus or inside of an atom. And they're called the strong nuclear force and the weak nuclear force. Those are the four. Gravity, electromagnetism, strong and weak nuclear are the four forces that we can use to explain everything that happens at this point, as far as we understand. So let's talk about them for a little bit. Gravity. We'll start with gravity because it is the weakest of the four known forces. And it's not even just a little bit weaker, it's an incredibly lot weaker. Okay? And gravitational force is an attractive force between any two objects in the universe that have mass. You have mass, you've got gravity. You have attraction. Okay. That's the acceleration of gravity on the surface of the Earth, actually. So that's not force, that's acceleration. Okay?
But the force of the Earth is equal to the gravitational force of the Sun.
No,
Second force that I want to talk about is the weak nuclear force, also sometimes known as the weak interaction. This is a force that's involved with radioactive decay, which is a subject we'll talk about next year, where we get into half-lives and alpha, beta, and gamma decay. It is a lot stronger than gravity, 10 to the 26 times stronger than gravity. So that's 100 million, billion times stronger than gravity. Okay, so that's a lot stronger than gravity, or maybe 1,000 billion, but no, or 100 billion. I don't know if I'm getting that right. It's a lot stronger. This is the weak nuclear force. Okay, we'll talk about this a lot more next year. I don't know, a lot though. Okay, then we move up to the electromagnetic force. The electromagnetic force is even stronger yet. That's just weird. Okay, what? Wait, I got to get through this slide though. I don't know. I'm going to say no just for fun, but I don't really know. Okay, so the electromagnetic force is even stronger yet. And the electromagnetic force is a force that any object that has electric charge experiences from other objects that have electric charge. Okay? So on an atomic level, there's a lot of electromagnetic force happening because in an atom, we have electrons, which are charged, and we have protons, which are charged. So they're always exerting forces on one another, and atoms are also exerting forces on other atoms. So on an atomic level, there's a lot of electromagnetic stuff going on. Okay? The fourth and final and most strongest of the forces that we know at the moment is called the strong nuclear force, or the strong interaction. And I just made that freeze in a very strange way. Come back. There we go. Okay, it is 10 to the 39 times stronger than gravity, and it is what holds the nucleus together in the atom. And think about this for a second. What do we find inside the nucleus? Protons and neutrons. What kind of electric charge do neutrons have? None. That's why we call them neutrons, because they are neutral. Protons, however, have charge, correct? And we call it positive charge. Think about that for a second. What do similarly charged objects want to do? They want to repel. So here you have these protons that are similarly charged, and we've packed them into a really small area. They don't want to be there in terms of the electromagnetic force. The electromagnetic force is trying to rip them apart, but they don't go flying apart because there's an even stronger force called the strong nuclear force holding them together. When you mess with the strong nuclear force and rip them apart, things happen such as like atomic bombs. Exactly. Okay.
How do they kill the strong nuclear interaction? Explain the concept of atomic bombs.
Yeah, no problem.